All right, we have been looking at how computers can represent different types of information in binary. And last time we looked at how we can represent positive integers and positive decimal numbers in binary. Now we haven't looked at how to do negative numbers. That's outside the scope of this course. If you were to take like a discrete math course, you would learn about that in that course if you go on in computer science. So you will get a chance to learn that. This is just kind of an overview so that you get an idea of how things can be represented in binary. So you have the basic idea of how integers and decimal values can be represented in binary, and today we're going to look at how letters or characters and strings of characters can be represented in binary as well. Okay, so to represent characters in binary, we use something called the ASCII code or ASCII table. So ASCII stands for the American Standard Code for Information Interchange, and we just pronounce it ASCII. It's an acronym. And so if you look, this is an ASCII table that tells us the value that the computer uses and what it means. So one thing to notice about this table is all of the values here are given in hex. Okay, and so hex is short for hexadecimal. Okay, and hexadecimal is the same, is just another what we call base 16. So the base 16 number system is called hexadecimal. Okay, and typically if you find ASCII tables, most of the time they will give you the hexadecimal value and then the character that it represents. So these don't look very familiar to you. A lot of these are just control characters, and so you don't really need to worry about those too much. But then when we get up here in these characters, we're looking at some punctuation and symbols, parentheses, some math operators, and then we get to numbers, our digits actually. Okay, and then we get to the capital alphabet here, and eventually lowercase letters here. Okay, and so these would be for 8-bit representation of characters. Okay, so if you were to count these up, there's 128 different values here, and it takes 8 bits to represent 128 different things. Okay, so each one of these would be written out as an 8-bit string. So we just need to look at today basically how to convert from hexadecimal, which is what's usually given in an ASCII table, into binary. Let me show you another version of the table. So this version of the table kind of groups the characters into control characters, which are mostly these ones, and then there's one at the end that's a control character as well, into printable characters. Okay, and these ones here, these ones are our 8-bit characters, or 1 byte. And then they have also extended ASCII to handle more than 128 different characters, to handle some letters from other alphabets, not the English alphabet, but some foreign alphabets and that kind of thing. So we will only really be looking at 8-bit characters, but you can see that there's a way to extend it to go into other characters as well. One thing to notice about this table, though, for example, let's just look that A has a value of 65 here in this table, capital A, and in this table, capital A has a value of 41. Okay, so this is telling you this is hex. This doesn't tell you, but this one is actually a decimal value. So these are decimal values. So if you use this table, make sure you recognize these are decimal values. If you use this table, make sure you recognize that these are hex values because that makes a difference. It's a different number system. Okay, so let's talk a little bit about hexadecimal. In fact, if you find an ASCII table, usually you'll find it in hexadecimal, and most computer scientists would find it more desirable to have it in hexadecimal. So let's kind of look at why that might be true. So as I mentioned, hexadecimal is the number system that uses base 16. It's a positional number system. It uses base 16, so there have to be 16 different symbols. So that will be 0 through 9. That's 10 symbols. And now we've run out of digits that we recognize for typically writing numbers, and so we've borrowed some characters from the alphabet. So we use A to represent 10, B to represent 11, C 12, 13, 14, 15. That's 16 different symbols. And then because the base is 16, the place values, okay, the weight of the different characters will be 16 to the 0, 16 to the first, 16 squared, etc., because it's base 16. So remember, we had 10 here when it was the decimal system. We had 2 here when it was the binary system. Since this is base 16, we have to put 16 there. Okay, so let's say we wanted to find the binary representation of A. Well, as I mentioned, normally we would go to this table in hexadecimal. Okay, find the letter A. Here's capital A, and that has a hex value of 41. Okay, and so the way that you often see hexadecimal values written is 0x. That signifies that this is a hexadecimal value, and then 41. And we would call it hex 41 as opposed to 41. 41 makes us think of a decimal number. Okay. So, but this is a hexadecimal number, base 16, and it has 4 in the 16's place, and it has 1 in the 1's place. Okay, so this is in the 16 to the 0 place, and this is in the 16 to the 1's place. Now, if I wanted to convert this to a decimal number, I can do this the same way that I've converted other numbers, like in base 2. So this would be a character that represents a value of 4 times its place value, which is 16 to the first, and then 1 times 16 to the 0. So this is 64, and this is 1, so that would be a decimal value of 65. And then notice in this table that gives us decimal values that A has a decimal value of 65. That's a decimal value for A. Now, of course, our goal was that we really wanted to convert this to binary. We know that it's 65, and we know how to convert decimal numbers. This is a decimal number, base 10. We know how to convert decimal numbers into binary, so we could go ahead and follow that process. So we could take our number 65 and then use repeated division by 2. So divide 65 by 2. Well, 2 goes into there 32 times with a remainder of 1. 2 goes into 32 16 times with a remainder of 0. Into 16 8 times with a remainder of 0. Into 8 4 times with a remainder of 0. Into 4 twice with a remainder of 0. Into 2 once with a remainder of 0. So that, if we read it down, will give us the binary representation of the number 65. Okay, so that would be 1, and then 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 zeros, and then a 1. Now that's a total of 1, 2, 3, 4, 5, 6, 7. Okay, and in ASCII, we would actually have to use 8 bits and fill up a whole byte. So you can just put leading zeros on anything to make it into 8 bits or 1 byte. Okay, now I said that typically you will be given an ASCII table in hexadecimal, and it might seem to you like, wouldn't you rather have it in decimal? Because if I give it in ASCII, I have to convert to decimal, and then I have to take the decimal number and convert it into binary. And if I had the decimal, I could skip this step and I wouldn't have to do this long thing. And it might seem at first thought that that's a good idea, but this is a very slow way to convert from hexadecimal to binary. We don't actually have to go through the decimal if you know the simple, fast trick of converting between. Okay, so if I look at these 8 bits and group them into groups of 4, and then consider the 4 bits separately. So if this is the ones place, and so this is the number 1. Over here, this is the ones place, the twos place, the fours place. This is the number 4. Okay, 4, 1. Hopefully that looks familiar to you. That's the hexadecimal value. Hexadecimal value 4, 1 is the same as if I put these in groups of 4 and look at the binary representation of the first hexadecimal character, and then the 4-bit representation of the second hexadecimal character. Okay, so that's why we're given the table in hexadecimal, because the conversion doesn't involve any kind of repeated division. It's just a very fast substitution of 4 bits for each hexadecimal character. So suppose we wanted to convert from the hex 4C into binary. Okay, so we're going to replace each of these hexadecimal characters with the 4-bit binary representation. Okay, so I'm going to take the 4 and replace it with 4 bits. Okay, so we can even look at that up here. That was 0, 1, 0, 0. Okay, and then we'll take the C and replace it with its 4-bit representation. Okay, now C, that's a little tricky, so let's go up here and look. So C, think of this as 9, 10, 11, 12. C is the 12th character, so that's like the number 12. So here you want to think 12. So if I wanted to represent the number 12, 12 is the same as 8 plus 4. So I would need something in the 8's place and something in the 4's place, but nothing in the 2's place and nothing in the 1's place. Okay, so 1, 1, 0, 0 would give me the number 12. And so so now I have the 8-bit binary representation. So 0, 1, 0, 0, 1, 1, 0, 0 base 2 is the same as the hex number 4C. So very quick and easy conversion from hex to binary. And of course, if you just run that process backwards, it's very easy to convert from binary to hex as well. So to convert from binary to hex, you would just take and divide your number into groups of 4, and then replace each group of 4 bits with the equivalent hexadecimal digit. Okay, and so if we look at this one, this is the 1's place, the 2's place, the 4's place. This is the number 6. This is the 1's place, the 2's place, no 4's, but we do have an 8. That's 11. So 11, let's go 9, 10, 11 is B. Okay. And so the hex value B6 is the same thing as 1, 0, 1, 1, 0, 1, 1, 0 in binary. Okay, so notice that's much easier because there's none of that repeated division, and it should go much more quickly. That's why you're typically given the ASCII table with hex values as opposed to decimal values. With decimal values, you'd have to use that repeated division, and it's just longer. Okay, so let's look at some examples now. So we've looked at how to represent a single character like A in binary, but what about if we had strings? of multiple characters. So let's say we want to do this word, code. So or lowercase c, lowercase o, lowercase d, lowercase e. Well, as you can imagine, we're just going to do the 8-bit representation for each letter. Okay, so we would want the 8-bit representation for lowercase c. Well, before we'll go here, they give us the hex value. So C is a hex 6-3. So this is going to be 6-3. The lowercase o is 6F. The lowercase d is 6-4. And E comes right after D. It is 6-5. Okay, so that would be the hex representation. So this is in hex. And to put it into binary, I just have to replace each of these hex digits with the 4-bit binary. Okay, and so I'm going to go this way, I think. So let's do 4 bits for the 6, 4 bits for the 3, and then we'll have a 6, and then an F, the 6, and the 4, the 6, and the 5. Okay, so 6 is 0, 1, 1, 0. 3 is 0, 0, 1, 1. Every time we see 6, it's going to be that 0, 1, 1, 0. It's 2 plus 4. F, okay, so F, that's the 15. That one you might need to do on the side or whatever, but 15 is divisible. It goes 7 times into 15 with a remainder of 1. It goes 3 times into 7 with a remainder of 1. 1 time with a remainder of 1. So 1, 1, 1, 1. That's a good one to memorize. F is all ones. 6, we've seen that one before. Okay, 4, that just has a 1 in the 4's place, no other place. 6, and then 5 is a 4, oops, and a 1. So 0, 1, 0, 1. Okay, so that would be how a computer or a machine would represent the word code written in all lowercase letters. Okay, we're going to do the word code again in all capital letters just so that you can see they're different. Like the capital letters and the lowercase letters are different. So if we did capital C, capital O, capital D, capital E. Okay, oops, I'll put the hex down here. Okay, so capital C is 4, 3. Capital O is 4F. Capital D is 4, 4. And capital E is 4, 5. Okay, so one thing to notice is that, you know, these, the 3, the F, the 4, the 5 are the same. So you might have looked at this and wondered, well, why do they have all the capital letters and then this stuff in between, and then they start the lowercase letters? Why didn't they just put the lowercase letters next? And it was to give this kind of symmetry. It makes it easier to do certain things by looking at, you know, the upper, just the top bits to tell whether it's a lowercase or uppercase, that kind of thing. So they organized it to do so that the hardware could work efficiently and know both of these things are types of letters. Okay, so once again, we're gonna put our 4, our 3, our 4, our F, our 4, and 4, and 4, 5. Okay, so 4, we've already seen that one before. That's 0, 1, 0, 0. Let's go ahead and fill that in for all of our 4s. Okay, 3, that's 1 plus 2, and we've seen that before. F, we've seen that one before. And 5, we've seen that one before as well. Okay, so that would be the binary representation of the word code written in capital letters. Now here is an interesting one. Let's say we want to do this string containing the character 1 followed by the character 2. Okay, so if we go to our ASCII table, here we find the character 1 that has a 3, 1 as its hex representation, and then 2 has 3, 2. Okay, so this would be the hex. All right, so this one, we'd have to put a 3, 1, 3, 2, and use the 4-bit representation in each of those. Okay, so 3 is 0, 0, 1, 1. 1 is 0, 0, 0, 1. 3, once again, is 0, 0, 1, 1. And 2 is 0, 0, 1, 0. Okay. And so, the string that contains the character 1 followed by the character 2 in ASCII would be 0, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 0. So one thing to note, okay, this is absolutely not the same as the number 12. Okay, because note 12 in base 10, that would just be 1, 1, 0, 0 in binary. This is not 1, 1, 0, 0 in binary. So a string of characters containing the character 1 followed by the character 2 is not the same as the number 12, which means, you know, a dozen things. So those are very different things, and the computer will treat them as very different things. Okay, if you added the character 1 and the character 2, you would not get the character 3. You would not get the number 3. It doesn't. These are characters, and they're very different than numbers. And once we start looking at Python, we'll see that Python differentiates between a character 1 and a number 1 as well. And this is why character 1s are represented in ASCII in a certain way, and it's very different than the way that numbers are represented, right? ASCII is not the same as, you know, if you look at the number 1, it does not have a value of 1. It has a hex value of 31, or a decimal value. Here's our 1. A decimal value of 49. Okay, it's not 1. So that's just a good thing to remember. Okay, let's do our last one so that we can use some of these other special punctuation and pound sign kinds of things. So let's say we had this pound sign wow, or hashtag wow. Okay, so if we go to our table, the pound sign / hashtag is 23, or 23, I guess I should say. The capital W is 57. The lowercase o, we've seen that before, that's 6F. The lowercase w is 77. And the exclamation point, you've probably found, oh, there it is. The exclamation point is 21. Okay. And so, to represent this, let's see here, we need the 2 and the 3, the 5, 7, 6, F, 7, 7, a 2, and a 1. So 2 is 0, 0, 1, 0. 3 is 0, 0, 1, 1. 5 is 0, 1, 0. 7 is 0, 1, 1, 1. 6 is 0, 1, 1, 0. F is 1, 1, 1, 1. 7 is 0, 1, 1, 1. 7, 0, 1, 1, 1. 2 is 0, 0, 1, 0. And 1 is 0, 0, 0, 1. Okay, and so that is how we would do our hashtag wow in ASCII. And if we had that stored in the computer, it would know that that's what that meant. Okay, so we've looked at how to represent numbers in using only binary. We've looked at how to represent characters and even words and strings of characters in binary. So you can imagine we could just extend this out and we could represent entire books, you know, all using only ones and zeros by just going through this process. All right. So next time we will look at how to represent instructions using only ones and zeros.